Hello and welcome to my channel. In this video I'm going to be testing these various different devices, all made in China of course. Top one is a network analyzer, or VNA, and these are two spectrum analyzers. This one costs maybe $60 or $80 and that one costs about 3 times as much, or maybe a little bit more, depending on where you go shopping. And I'm just going to compare using them as signal generators, which is not what their designed purpose is. This is for analyzing RF networks connected between the two ports, and these two are supposed to be looking at signals to display their spectrum connected to one or the other of the input ports. But they all have a signal generator function which I want to use, and I want to do tests at 869 megahertz because that's close to the Meshtastic frequency where the interest still is. And I'm going to use my favorite receiver. This is SDR console version 3.3. It's my favorite SDR receiver application. It's running on Windows, and the actual SDR itself is my favorite receiver hardware, which is this SDR Play RSPDX. It's the version 1. The version 2 came out and I haven't bought it yet, but it I think only offers better noise performance at very low frequencies, so it's not the end of the world. And I'm going to be using this at 869 megahertz. The input antenna A has got this little dipole. That's one of the best antennas I have. I bought a load of these and then trimmed them to work at the right frequencies. If you watch my earlier videos, to make them resonate closer to 869 megahertz than they were when I bought them, but they were super cheap. I think that was like $4 from a shop online. Amazon sells them for 3 times as much money, but you often have to open them and trim them. Anyway, all those different brand names don't mean anything. I think they all come out of the same factory in China with poor quality control, which reminds me I just had to fix my selfie stick because it was only held together with super glue, it turns out, and it fell apart. Luckily the phone didn't hit the floor. Anyway, thank you China, cheap stuff. So this attenuators for other tests later. So the first part of the video I'm going to be looking at the frequency accuracy of these outputs of the signal generators, and in the second part of the video I'm going to try and measure the output levels. And of course all of this equipment is not calibrated against any super duper standards at all. It's as it was out of the box. I haven't tried to change the frequency or amplitude calibrations at all, so probably I could do that if it seems to be necessary. So this is the 869 megahertz frequency I've chosen to use because I can remember it. This is -3 kilohertz and that's +3 kilohertz. So I was looking at a 6 kilohertz bandwidth just to see how accurate the frequencies are. And the center frequency is 869 megahertz. So the first thing I'm going to do is I'm going to show you how to make one of these devices into a signal generator. This is the VNA, NanoVNA-F version 2, which is very nice. I probably won't be able to find the menu now. So that's doing its VNA thing, sweeping, and in fact you know it's sweeping because you can see this pulsing signal at 869 megahertz as the VNA sweeps through the range. I think it's going through a range of, well, it's going from 860 to 870 megahertz. So it's sweeping a 10 megahertz range, and at some point goes through this narrow bandwidth here. And this is transmitting, as it were, using this antenna, which is currently measuring the SWR of, which is 3.3, because it's laid down on the desk and detuned. These other two devices also have antennas on it, whatever I had lying around. Anyway, I want to use this as a signal generator, so I have to try to remember how to do that. Hit the menu, and how did I find that? Oh, you have to go to stimulus. Well, it's not easy to do this. Stimulus, and then if you look at the stimulus menu where you normally set frequencies, there is signal generator, which gives you a signal generator. It doesn't store the settings from one usage to the next, unfortunately. I could save it probably in a menu, but it would be nice if it would just remember it. Anyway, so what do? We want the frequency to be 869 megahertz, and let's set the output level as low as it goes, which is -9 dBs, which means 9 dBs less than some unknown value, which we're going to measure later. 0 dBs will be equal to that unknown value. We don't know what that is yet. So it's the minimum anyway, -9 dBs relative to something. And let's turn it on, RF out on, and hopefully a signal has popped up on the receiver. And there it is. And it's slightly outside my 6 kilohertz bandwidth that I was looking in. So it's not exactly 869 megahertz, is it? What I can do is I can just change the frequency of the receiver slightly using the trackpad on a laptop. That's currently 869, so let's go down in 1 kilohertz steps. So it's 868.999, 998, 997, 996 is a bit too far. So it looks like 868.997 when the signal source thinks it's generating 869. So it means it's 3 kilohertz low on frequency output. As I say, I've never calibrated the frequency, it's out of the box. So it's 3 kilohertz low, which is a small percentage of the 869 megahertz frequency, but there we are. This is actually the worst of these three devices, because I already checked them previously. This is the worst one in terms of frequency calibration out of the box. So minus 3 kilohertz. These are manufactured by companies in China, of course, because the hardware is open source and the software. Guy in the Netherlands has designed it and open sourced it, which is very nice. So there are lots of different factories pushing these things out, made in China with various prices. You can get original good ones and you can get copies of bad ones, and the prices can be very low, especially this one. A friend got one of these direct from China and it was extremely cheap, but it had all kinds of little problems. So I think he sent it back in the end and got a refund. So you have to be careful who made it and whether it's an original. Some of these are made by CC, that's SEESII, I think is the manufacturer. And there's also a manufacturer called SDR Geek. I think they make them. You're never sure if they're a maker or a seller. And these are available on Amazon in Europe, UK. If it's still in Europe, I don't know. Probably not. So yeah, check which manufacturer the devices are. And usually you get what you pay for. So the more money they cost, like this is quite expensive, but the closer it is to the original design using better quality components, as we'll see later as well when I look at the amplitude outputs, the signal level output. And so this one is 3 kilohertz low, coming out at 868.997 megahertz. So let's turn the RF output off and check that it really has gone off. Yeah, the little signal's disappeared. Move down to the next one. And if you, I'm not going to do it, but you hit the button that says menu on the menu, mode. And when you hit the mode button, it pops this up. And what you do is you select, I want to do high out. That high means the upper output and low is the lower output, nothing about anything else, high and low. So I want the high output, which is the higher frequency range, in fact, and output, not input, because I'm not looking at a signal spectrum. I'm generating a signal here and pushing it out, which is not what the device is really designed for, but it works. Looks like it's going to be a square wave by the look of it. Anyway, so it says return to, because that's the last thing I did, whereas switch to is not the last thing I did. Interesting logic in this software. So let's do high out. It's currently off. Frequency is set to 869.000 megahertz. The level is 0 dBm, and this really does mean 0 dBm, not just dBs. So it's dBs relative to 1 milliwatt. So 0 dBs relative to a milliwatt is 1 milliwatt. So that's the theoretical output coming out of here. 1 milliwatt of RF power. No modulation, no sweeping, no calibration factor called external gain. So it should work. So let's press the button. Now it's on. And oh, there it is on the receiver. And it's outside that green box because that's set 3 kilohertz low. So I'm just going to increase the frequency back to what I was looking at, which is 869.000, and you can see that it's that signal source is slightly higher frequency. Let's just go 1 kilohertz further. Plunk. So now it's plus 1 kilohertz, and that's pretty much centered in that bandwidth. So it means there's a 1 kilohertz offset from what it should be generating. So this little cheapest device, spectrum analyzer, is generating a signal at this frequency plus 1 kilohertz, which is, yeah, better than this one that was minus 3 kilohertz. So it's a little bit more accurate, but I think it's just a lottery really how well these are calibrated. It's not talking about the quality of the device, it's just who was doing the calibration that day. Maybe this one's a Friday afternoon job. Hopefully I can recalibrate it later when I get a decent frequency standard to measure these things against. So that's that device, and we'll see later what the possible output power levels are. So currently 0 dBm, which is 1 milliwatt, for those of you watching in black and white. No, that doesn't work, does it? So let's turn that off. I'll show you what happens on the receiver as I turn it off. So I'm now going to press the button that says on, which means the current state, not what you're going to get. Press it, and boom, the signal's gone away. And now the button says off, which is the current state, and it's not what you're going to get when you press it. That always confuses me with these things. Opposite logic. Anyway, moving on to the third device. This is the spectrum analyzer that costs a bit more money than the very small one. This is a Ultra or Tiny SA Ultra. An Ultra means it's got a bigger screen, it's a little bit heavier, probably got a bigger battery in it, also has a higher frequency range. I think this one only goes up to 1 gigahertz or so, I can't remember. This one goes up to 4 or 5 gigahertz depending on whether you put the magic pin number in to extend the range. And the output from the signal generator function comes out on the lower port, which is not the upper port of the smaller one, so you have to know these things. Otherwise you wonder why there's no signal. So again, I press the button that said mode in the menu. Mode takes you to this little menu where you can choose what you want to do, and I want to do signal generator, not spectrum analyzer, so I just click on that, and then I've got my signal generator, and it's remembered I wanted 869 megahertz, which is very nice, and the level is currently minus 19.5 dBm. Let's call it minus 20 dBm. So that's what's that, 1/100th of a milliwatt. No modulation, no sweep, and no calibration factor. Output's a square wave. I hope it's not. Anyway, so let's press the button, and I'll show you the screen as I press the button that says off in order to turn it on. So here's the screen, listening slightly off frequency. Bing. Oh, look at that. This is set to 1 kilohertz high of the intended frequency, and this looks a bit high too. So let's just decrease that down by 1 kilohertz to give 869.000, which is where I'm trying to do this experiment. And you see the signal is bang in the middle of that 6 kilohertz bandwidth. So it looks like the frequency calibration of this Tiny SA Ultra agrees very accurately with my RSPDX SDR receiver, which might be correct as well. So could be a happy coincidence, but it looks like this device has the best frequency accuracy, probably. So it's a Tiny SA Ultra compared to the normal Tiny SA without the Ultra, which was 1 kilohertz off, and then this vector network analyzer is 3 kilohertz off. But then when you measure filters and things and antennas, you don't need accuracy of kilohertz at all. So it's not perhaps so important that it's accurately frequency calibrated. I haven't looked up the spec to see what the spec is. So there we are. That's the frequency calibration of those three devices. And I'm going to pause the video for a second, and then I'm going to continue by trying to measure the output level of these devices. I'll use a spectrum analyzer to do it, not the RSPDX receiver, because I don't think the output's very calibrated. They say it is, but I haven't tried it yet, so I'll use one of these. Switching now to measuring output levels from these devices. First one I'm going to use to measure is the output from this vector network analyzer in signal generator mode. RF out is switched on. The level is set to 0 dBs relative to something we don't yet know what it is. And I haven't connected it directly into the spectrum analyzer because I want to protect the input from overload. As you'll see later, this device produces quite a lot more power. So I put an attenuator in line. I could have used a smaller attenuator, which is 10 dBs, but actually it's not quite enough attenuation to protect this device. These devices have maximum input levels printed on the front. If you can read it, it's very small and faint. Maybe 6 dBm, or some of them are, well, they're various, but I don't want to get anywhere near that power level because you risk burning out the input stage, so I always have an attenuator. 10 dBs is not quite enough. This is a 40 dB attenuator, which you can also handle a bit more power. This one can handle up to 15 watts, and that one only 2 watts, but I don't think any of these devices generate anywhere near that much power, but it's always good to be on the safe side. So that's a 40 dB attenuator there, and this is currently switched on. It's generating its output signal coming into the better spectrum analyzer, the Tiny SA Ultra. And what I've done here, to compensate for the 40 dB attenuation, what you have to do is tell it you're using that if you want this amplitude reading to be correct. So what you do is you set the external gain, and in this case minus 40 times 1 gives me an external gain of minus 40 dBs. So it takes that into account and then displays an output level which is actually true to what was presented to the input of the 40 dB attenuator. So it's using the marker, just move around to find the maximum, which is 869 megahertz approximately, minus 3 kilohertz, which is actually reflected in this display here. It's actually showing about 3 or just less than 3 kilohertz low, which is what we already measured. There was an error here. So it looks like the frequency calibration of this network analyzer agrees with the RSPDX SDR in terms of frequency. Let's make the menu go away. So what have we got coming out? We've got that frequency, and it's minus 10.9 dBm. It's fluctuating a little bit. There's actually a 1 dB loss through this setup with the attenuator and the cable. So that 1 dB probably accounts for the difference here of about a dB. So this is probably a roundabout meaning. It means minus 10 dBm is coming out of this device. So its output level is minus 10 dBm on signal generator mode when you set 0 dB maximum power. And what I'm going to do now is go to minimum power, which is minus 9 dBs. It goes in small steps. I'm not going to try and measure those. So let's just hit minus 9 dBs. So output power should have dropped by 9 dBs, which is nearly 10. So what's coming out? What are we measuring now? Measuring minus 19.9, fluctuating. Call it minus 20, and then there was a 1 dB loss in the cabling and so on. So it's about minus 19 dBm that's coming out of that top device. Previously it was generating approximately minus 10 dBm, and when you put in an extra 9 dBs of drop in output level, minus 10 dBm drops to minus 19 dBm. So it seems to agree with itself that the calibration of this output level setting seems to be roughly correct, which means it has an output level of between minus 10 and minus 19 dBm. And of course minus 10 dBm is 1/10 of a milliwatt, minus 20 would be 1/100th of a milliwatt. So that's the range of output levels that can be generated by the NanoVNA-F. Maybe it's different at different frequencies. I'm not going to check that because I'm only interested in 869 megahertz today. So that's the first device checked. What I'm going to do next is to test this device, see what the output levels are. So I'm just going to pause the video. I've connected this second device to the attenuator, 40 dB attenuator, and same as before, I haven't changed any settings on the spectrum analyzer to measure the output level. And I've started at the highest output level this can generate, which is plus 9 dBm on this tiny SA device. So it's almost 10 milliwatts. It's quite a lot of power for a tiny test instrument. So plus 9 dBm allegedly. And then I'm measuring that on here. And what do we see? Looks like 10 dBm indicated there. And I know I've got 1 dB loss in addition to the 40 dBs here. So it looks like this output level of plus 9 dBm is fairly accurately true, as I can see here. So what I'm going to do now is reduce the output power from this device, and you can do it by sliding along this scale, but it's a bit weird because it jumps. So that's 0 dBm output, which is 1 milliwatt. And what am I measuring down here? Minus 1.4 dBm. So again, with a 1 dB loss, it's about, well, we don't know, maybe half a dB wrong, but that's pretty good for this kind of test equipment if it's true. So the 0 dBm output seems to give 0 dBm. Let's slide down a bit more. That's minus 5. I want something else, and you can't have it. You keep sliding, and then suddenly jumps to minus 25. There's a big jump, which is to do with the attenuators and the switching inside this device, or maybe it's faulty, who knows. Anyway, so minus 25 dBm, and what's being measured is minus 17, or maybe minus 16, so it's not really coinciding very much with what I've chosen with the output. What was that? Minus 17 when I set minus 25. Let's slide it down a bit further. Minus 30 dBm, 31 dBm, and it's giving minus 20. So there's a 10, 11 dB error there, 12 dBs. There's something strange about the output level setting of this device. So from maximum output down to before the jump, the attenuator steps seem to work. I think there were 3 dBs. I checked them, and it coincided quite well on measuring. But when you go down after the jump to the lower levels, then what comes out seems to be unrelated to what you've chosen. That's minus 20. Let's go down to the minimum power, which is, what is that? minus 36 dBm, and now we've got an output level of minus 24, so it's gone down a little bit, 4 dBs, but not as many as I chose. I actually had this problem with another one of these devices. I actually sent it back. I bought the bigger version of that, which is this, and it was faulty, and it had the same problem that when you reduce the output power level, it didn't actually drop, but also the maximum power level was nowhere near what it said it was. So it had some serious problems, and after discussing with various people like the manufacturer and the inventor, it went back to Amazon and got fully refunded. And I just ordered the same thing again, which is this one, and this one works fine. So it does prove that the problem was the device, not me, because you never know. So this calibration here is all wrong. Minus 36 dBm is coming out actually at minus 24 now, so that's not the best. Anyway, let's try and measure this device as a signal generator with output power level, and the only thing I can measure it on is this device, which is sometimes a bit dodgy in terms of its measurements, so maybe not the best, but let's try it anyway. I have changed the test setup now so that we can measure the output power level of the Tiny SA Ultra, and the only device I've got to measure it with is the cheap, smaller Tiny SA with the dubious attenuation on the output level. So let's see what's happening. The frequency is set up right, 869 megahertz. Level is the maximum, which is minus 18.5 dBm. What I'm going to do to make it easier is just make it minus 19.5 dBm, which is close enough to minus 20. Let's call it that. No modulation, no sweep. So that should be generating approximately minus 20 dBm. And this goes through the 40 dB attenuator again into this measuring device, and I've already in the menus put in the external gain as minus 40 dBs to compensate for the attenuator, and you can see it's receiving, oh, I've got the big display on, so it's minus 21.9 maybe dBm with minus 20 allegedly being generated. So it's again with the 1 dB cable loss in here, it's within 1 dB accurate, so minus 21 approximately. What I'm going to do now is I'm going to go down in steps, because on this one you can click on minus 10 dBs and you get minus 29. So we're going down in 10 dB increments, and this has gone down to minus 31, which is what you would expect. Let's go down another 10 dBs, minus 41. This is working, minus 51. So every time I go down 10 dBs on the signal generator, then the measured output power is also dropped by 10 dBs, which is what you would hope it would do. Go down another 10 dBs, minus 60, another 10, minus 70, and it's generating minus 70 approximately. So it really corresponds quite well. Problem now is we're hitting the noise floor on the signal spectrum analyzer. Maybe I could push that down a bit by changing the resolution bandwidth, but I'm too lazy. If I go down another 10 dBs, which is minus 80, of course it's gone into the noise, because the noise floor is at minus 77, 78, so that's not a valid measurement. Let's come up 10 dBs again. So it looks like the Tiny SA Ultra, when you go down in 10 dB steps, the actual output power also changes by 10 dBs, which is nice. Unlike this one, where down to a certain value it was okay, but then lower, the output power didn't really change very much when it should have done. So this is not the best signal generator to use. This one is much better, and it's on frequency. This one's not bad, but it doesn't have the range of levels, and also the frequency is 3 kilohertz off. So what I've done is I've summarized those results here. And you can see that the Tiny SA, which is the worst one, has got an output level of minus 36 dBm up to plus 9 dBm, which is quite a wide range. And unfortunately, it's got some errors in the lower output powers. The Ultra version of that has got a much wider range that you can set of output power level, but not as high. It only goes up to this, minus 18.5 dBm and not plus 9, which is a lot. So this makes a good transmitter for testing antennas if you just leave it at maximum power. And also this one has the best frequency accuracy. And then using the VNA, then the range of output levels is very small. It's only 9 dBs in 1 dB increments, and the actual power level is minus 10 dBm. That's between these two, and my one's got a 3 kilohertz frequency offset. So that's the summary. So depending on the purpose you want to use these instruments for, you can choose the one that best meets your needs. And I'm going to perhaps go on and test some antennas next. Thank you for watching, and remember to like and subscribe, please.